Welcome back to The Explainer. Today, we're tearing down the walls of something most of us rely on every single day, but honestly, rarely even think about. We tend to treat databases like these magic black boxes, right? You put your data in, you ask for it later, and poof, it just magically appears. But under the hood, there is an absolute symphony of computer science happening. Okay, let's dive into this and break that illusion once and for all.
Think about the stark contrast between what a database actually is physically and what we demand of it. Physically, it's pretty simple. Just files on a disk, some memory structures, and a collection of algorithms. That's the whole shebang. But then you consider the immense pressure of the problems it absolutely has to solve. It has to guarantee blisteringly fast reads from millions of searches, juggle thousands of concurrent users without locking up, and provide bulletproof durability to survive a sudden power loss. It's a massive, almost unbelievable gap between what it is and what it must do.
So here's our roadmap for today. We're going to systematically tackle the speed problem, planning queries, safety and crashes, and finally wrap up with scaling up and out. Let's jump right into Act 1, the illusion and the speed problem. Now, what's really interesting about this is that fundamentally, the primary battle any database engine fights every single second is the agonizing bottleneck of disk I/O. Just think about the sheer scale of the performance gaps we're dealing with. Your CPU cache operates in nanoseconds. RAM operates in microseconds. But the second you have to go down to an SSD, or even worse, an old-school physical hard drive, you're suddenly operating in milliseconds or slower. To put that into perspective, in computer time, dropping from RAM to a disk is literally like going from driving a Formula One car to crawling on your hands and knees. This is exactly why databases rely so heavily on something called a buffer pool. They aggressively cache frequently used pages of data right in your RAM, doing everything possible to avoid touching that slow disk.
But what happens when you have to search for something specific across, say, millions of rows of data? Well, if you do a sequential scan, you're reading every single page. Imagine trying to find a specific mention of a historical figure in a massive 1,000-page textbook, but the book doesn't have an index at the back. You'd have to read every single page from chapter 1 until you finally stumbled across it. It is incredibly, painfully slow. An index scan, though, that changes the game entirely. Just like a real book, it uses specialized data structures to let you jump directly to the exact page you need. And the absolute king of these specialized structures is the B tree. It is the ultimate speed hack. Why? Because unlike standard data trees that grow super deep, B trees are designed to be extremely wide and shallow. This perfectly minimizes those expensive disk reads we were just talking about. The lookup process is wonderfully simple. The database starts at the root node, compares your search value, follows the pointers down the wide branches, and instantly reaches the exact leaf containing your data. It takes a search of a billion rows and turns it into just 3 or 4 lightning-fast operations. It's brilliant.
Moving on to planning the perfect query.
Here's the catch, though. Simply having an index isn't enough. The database actually has to figure out the fastest way to use it. This internal pipeline is fascinating. First, your SQL query arrives. Then, the SQL parser translates your text into a format the machine actually understands. Next comes the query optimizer. And I really want to emphasize this. Building a good query optimizer is widely considered one of the hardest problems in all of database engineering. Its sole job is to analyze your request and generate the absolute fastest execution plan to go fetch your data.
So how exactly does it pull that off? By acting like an incredibly fast, highly mathematical brain. Modern databases use what's called cost-based optimization. Before making a single move, the optimizer looks at some very specific metrics. It estimates the row counts it needs to touch, the number of disk grades it's going to require, the CPU cost, and the memory usage. It calculates the quote-unquote cost of every possible way to find your data, whether that's an index scan, a full table scan, or some complex join, and it ruthlessly chooses the cheapest, fastest path available.
All right, let's shift gears to Act 2, safety, ACID, and crashes.
I want to slow the pacing down a bit right here, because as thrilling as the quest for pure speed is, it means absolutely nothing if your data gets corrupted or destroyed. We're transitioning from the world of optimization into the high-stakes reality of data corruption, concurrency, and sudden server crashes. This whole area is governed by a core guarantee, known as the ACID properties. Think of a standard bank transfer. If I send you $50, my account absolutely must go down by 50 and yours must go up by 50. If the server crashes exactly between those two steps, we have a massive problem. ACID prevents this. Atomicity means the transaction is all or nothing, both steps succeed or neither do.
Consistency ensures the data stays valid. Isolation keeps simultaneous transactions from messing with each other. And durability guarantees that once a transaction says it's committed, it survives, even if someone literally trips over the server's power cord.
So, the crucial point is, how exactly does the database guarantee that durability? The answer is a piece of absolute magic called write-ahead logging, or WAL. Before a database ever touches the actual data tables on the disk, it writes a record of the change to an append-only log file first. It literally writes ahead. If the database crashes a millisecond later, no problem. The system simply reboots, reads that log, and reapplies any missing changes. That log is your ultimate safety net.
But power failures aren't the only danger out there. Other users are a massive danger too. Let's picture the chaos known as the dirty read phenomenon. Imagine thousands of users colliding on the same system. In one moment, transaction A updates a row, but hasn't actually committed it yet. In that exact same millisecond, transaction B reads that row. But wait, transaction A suddenly fails and rolls back. Now transaction B is holding on to invalid data that technically never existed. This is an absolute nightmare for data integrity.
Now let's look at how this builds into one of the most brilliant solutions in modern computing, multi-version concurrency control, or MVCC. Instead of just locking up the database so users have to wait in line, MVCC fixes this by keeping multiple versions of a single row. Readers get a frozen in-time snapshot of the data, while writers are allowed to go ahead and simultaneously create brand new versions of those rows. It's this incredibly elegant dance. It allows readers and writers to work at the exact same time without ever blocking each other, which massively boosts performance.
And that brings us to Act 3, scaling up and out.
So we've made the system fast, and we've made it safe. But what happens when the sheer volume of data simply outgrows the physical limits of a single machine? We're talking about terabytes or even petabytes of information here. When you reach this scale, engineers have to carefully choose their database architecture based on some drastically different real-world workloads. For day-to-day banking or e-commerce checkouts, where you have millions of rapid, small queries, you use OLTP, online transaction processing. But if you need to crunch years of historical data for analytics dashboards and huge aggregations, you need OLAP, online analytical processing. You simply cannot use the same scaling strategy for both. They require entirely different fundamental designs.
And this brilliantly illustrates the ultimate trade-off in distributed systems. When you start splitting these massive workloads across multiple servers, you run directly into a mathematical wall known as the CAP theorem. It dictates that you have consistency, meaning the data is exactly the same on every server, availability, meaning the system always responds, and partition tolerance, meaning the system survives when the network connection between servers randomly breaks. The harsh truth of the CAP theorem: you physically cannot guarantee all three properties at the exact same time. You always have to compromise.
To navigate those impossible compromises, engineers use some massive scale tactics. They might use a primary replica model, routing all the new writes to one main server while replica servers handle the reads. They have to decide between synchronous replication, which is super safe but slow, or asynchronous replication, which is fast but a bit risky. And when a single table gets just too incredibly big, they use sharding, literally chopping the data up and splitting it across dozens of different machines. Spreading data out like this introduces an unbelievable amount of complexity, but for sure it's absolutely required to survive modern internet traffic.
Finally, we arrive at the foundation of the modern world.
As we bring this explainer to a close, it's so vital to pull all of these intricate, highly complex computer science concepts together into one cohesive big picture. Because at the end of the day, databases are not just passive files sitting quietly on a hard drive somewhere. They are an active, highly aggressive orchestration of the exact algorithms we've discussed today. The combination of memory caching, write-ahead logging, MVC snapshots, and B-tree indexing is literally what prevents global digital corruption every single second. It is the invisible, unbreakable foundation powering everything from Google-scale web services to global banking systems to the very cloud infrastructure we all rely on. So I want to leave you with this final crazy thought. Right now, as you stream this, how many invisible B-tree lookups, write-ahead log entries, and highly orchestrated concurrency protocols just fired off entirely behind the scenes just to load this exact explainer for you? This magic is happening millions of times a second, right under our noses. Thanks for joining me on this deep dive. Keep learning, and I'll catch you in the next.